Hey folks, welcome back. We're getting ready to crush the exam 3. We're getting ready to crush exam 3. And this time we are looking at a hanging cylinder problem. So our system is shown with this diagram. We have a cylinder with a cord wrapped around it, and it's attached to a fixed point on side A. On side C, on the right hand side, it is accelerating and moving upward, right? So the cord at E is moving upward at a velocity of 300 millimeters per second and is accelerating at a velocity of 480 millimeters per second squared. We're given that the cylinder is of radius r, and that radius r is 75 millimeters. In this problem, we are asked to find the accelerations at point C and at point D. Because this is a review problem, I highly recommend that you pause the video and attempt to solve it right now. So, welcome back. Hopefully you paused. If not, a few things to consider. So consider a couple of things. One, v sub a is 0. And that allows us to regard, or to not to regard, but to use the instantaneous center of rotation method for some of our calculations, right? So big picture, we should be able to relate the motion of C to the not motion of A to calculate some things. Number two, we would say A sub A, A sub C, A sub D have normal and tangential components. Okay, so if you were waiting for the hints, there they are. Again, I highly recommend that you pause the video, attempt to solve it on your own. There is no downside to doing that, and it will tell you if there's anything that you don't need to study. So here we go. All right, welcome back. Let's get to solving this thing. So let's see, this is our solution. And step 1, let's find the omega value. And we can do that using the instantaneous center of rotation method, right? So v sub c is equal to v sub e, right? And that is equal to it's r cross omega, right? So we would say r 2c from a times omega, right? If we were doing the actual cross product, omega would be over here, but we're not, so that's okay. And so that means that omega is equal to v sub e over r from a to c. Okay, well, let's see. That is v sub e is 0.3. I use meters because going from radians to meters is you have to go from meters to radians, not millimeters. So let's see, omega equals 0.3 divided by, and then this is twice the radius, right? So 2r, so 2 times 0.075, right? And what is that? That is 0.15. Under 0.3 is 2, right? So omega equals 2 radians per second in the anti-clockwise direction. Sweet. Okay, all right. Step 2. Let's just define the acceleration. So we'll define the acceleration of c with respect to point A, right? Again, using the fact that A is not moving to help us with solving this. All right, so let's see, what is that? That is A sub c is equal to the translational part, which is A sub A, plus the rotational part, which is A sub c with respect to A. Okay, and oh, by the way, with respect to WRT. So we need these in terms of components, right? So A sub c has an x and a y component. I note that there are nt components, but because the n component of these is going to be in a different direction, we need a coordinate frame that allows us consistency. So we use x and y. So let's see, this is going to be minus ACX, right? And that's in the I direction. It's minus because the acceleration is in the normal direction towards the center. All right, and then plus ACY, right? And this is just the A sub E, right? Okay, is going to be equal to A sub A x I plus A sub A y j, which it's not moving, so that's going to be 0. We'll get to that in a second. So then plus normal or tangential, doesn't matter. Let's do normal. So this is going to be, if it's the normal, then it is omega squared r, and where this is r c with respect to A, and the normal is in the j direction. Is that right? Yeah. Right. No, that's in the I direction. Sorry. Okay, then the tangential is, and you know what? Let me rewrite this as 2r, just because it's easier to see. So then this is 2r alpha in the j direction. Okay. So, right. Okay. As promised, this is 0. And let's see. I don't think we have a value for this. So this is ACX I plus ACY is this. So right. So plus 0.48 J is equal to AAXI plus, let's see, oh, we have values for all of these, don't we? So let's see, this is squared, so that's 4, times 2 is 8, times 0.1 or 0.075, 8 times 0.075, let's find out here. 8 times 0.075 is 0.6. So this is plus 0.6i plus, and 2r is 0.15 alpha to j. This, by the way, is negative. Has to be, because it's got to be accelerating this way. Okay, so let's see. We only have one variable in the j direction, so let's go that way. J direction, let's see, 0.48, and I'm going to go ahead and just divide this across, divided by 0.15 is equal to alpha, right? So that means that alpha is equal to 3.2. This is radians per second squared, and that is in the anti-clockwise direction. Handy piece of information, and that allows us to actually skip the I direction. And note, by the way, that we don't have a way of moving forward with consideration of the terms that are in the I direction, right? So we have ACX, AX, and a number. That's not going to be very helpful. So instead of doing that, we can use this to our advantage, right? So now we can just calculate ACX, right? Because ACX is defined by the so the motion of G is in the y direction, so we can use the radius of the cylinder to calculate the acceleration there using the alpha that we just found, right? And that is ACX is equal to, let's see, that's minus ACX is equal to R alpha, right? And that is equal to 0.15 times 3.2, right? Which gives us that ACX is equal to minus 0.3, and that is in the I direction, right? And we already know ACY, right? ACY is AE, right? So what does that mean? That means that AC is equal to minus 0.3I plus 0.48 J. One down, one to go. All right. Make some room here. So let's say we're on step 4. All right, so now we can just calculate A sub D, right? And we can do that because we have alpha. And I'll show you what I mean. Calculate A sub D. Now, what we'll do is we'll use a relative motion approach, right? So again, A sub D is equal to, and this time let's go with A sub G because it's straight up and down, and then the geometry is just quite a bit easier. A sub G plus A sub D with respect to G. All right, so we have this. I don't think we're going to need to break this into components. I think we have enough to solve this. So let's see, what is A sub G? Well, that is accelerating upward, and back to this idea of the instantaneous center of rotation, we can think of it like this, right? It is from A, just draw a straight line there. Wow, I really overshot that. There we go. There, and use this similarity idea to find the acceleration at G. Well, what is that? That is, this is R, right? And then it is alpha. So imagine if, and it's a little weird, but imagine if we just turn the arrow this way, right? And that allows us, it's a sort of, it's an inversion thing, but basically we can express the acceleration of g from the angular acceleration, right? So the acceleration of g is r alpha in the j direction. And so then we've got the normal and tangential of the acceleration of d with respect to g. So let's see, in the, so let's see, our r goes this way. So in the j direction, that's going to be normal. So we can do the normal. This is r omega squared, right? That's our normal plus our tangential, and our tangential is r alpha, right? So let's see, r is 0.075, and that is, we'll do this first, right? So a sub d is equal to 0.075 times alpha is 3.2. That is 0.24 I direction plus, and then this is the same thing, so 0.24 plus r times omega squared, so 0.075 times, was that 4 omega squared? Yep. So that's 0.3 in the j direction, and that means that a sub d is equal to 0.24 I direction plus 0.54 in the j direction. And there you have it. Okay, so big takeaways. It is of paramount importance to be able to use the relative acceleration to find your way through these problems. Whenever you're given the acceleration in a rotating system on one side and you need to find it in other places, you're definitely going to be using this relative acceleration. And you know, I think at the next problem we start looking at relative velocities as well. So I hope this was helpful. I hope you love the video so much you're going to tell your friends about it. And with that, I will see you in the next one.